I'm very glad to welcome you to the Sigma Xi lecture for the fall. Of course, it's been moved online. The Sigma Xi people sent me this nice special Sigma Xi mask. But today is representative of the Williams College Sigma Xi chapter, and our annual meeting has also been placed on Zoom, and we'll see how long the Zoom lasts. But in any case, I'm very glad that Professor Dwayne Daly has agreed to give his fall Sigma Xi lecture on Zoom. Our Williams College chapter, with me as president and Lois Banta, Professor Lois Banta, as secretary treasurer, has a couple of main activities each year. One of them is the lecture series in the fall and in the spring, of which Professor Daniel Alberts is scheduled to speak this spring. And then we honor our best, at Williams College, best thesis students with associate membership, which we hope gets converted to full membership eventually in the Sigma Xi, the Honorary Scientific Society. Professor Bailey is an alumnus of Amherst College and then got his PhD at the University of Massachusetts at Amherst. From there, he came to Williams about 22 years ago, and he is now working with his students on the relations of hardware and software and improving their relations. And I'm looking forward to hearing his lecture on that. Thank you very much, Wayne. Take it away. Wayne,
cool. Thank you. All right. Forgive me for any sort of strangenesses that might occur during this talk, but we're trying to make do with Zoom. Thank you for coming to the talk on such a beautiful day. I encourage us all to have a great weekend. We've had mountain days every week this month. I'm Dwayne Bailey in the Department of Computer Science. I'm a computer architect for the purposes of this talk, and I design computer hardware and computer software where they meet at the hardware-software boundary. I have been working with computers for a long time. So I started programming in 1965. And since then, I've really taken a great thrill out of making computers do things that they were not intended to do. So I've turned computers into radio stations. I've, harnessed them to break into themselves. I've done a number of interesting things that really gives you some insight into my personality. I just love ripping things apart and kind of challenging traditional notions of what computers and what software or programs are. So we all think we know what hardware and software are. Hardware is hard, software is soft. My first computer actually collapsed under its own weight. It was built out of cast iron, and software is something else. It's something more nebulous that you learn about, I guess, in various academic departments, and you go off and program hardware to do things you want. So you could sort of think of hardware as being the enabler for software. But those notions now are beginning to blur for a variety of reasons. And that's what this talk is about, is kind of thinking about why that's the case. So, all right. So I'm going to start off with thinking about where we've been recently. So we've had a long stint, certainly since those early days of 1965, we've had a long sprint, really, of building computers that are faster and faster every year, and thinking about how we can make software harness those computers to do more and more important things, more and more aggressive kinds of computations. And we all know about Moore's law. And so to a certain extent, what this talk is about is the end of Moore's law. So in 1965, Gordon Moore wrote a paper talking about cramming more and more components into smaller and smaller chips. And he predicted, in this graph we see on the lower left here, he predicted that we would be able to scale up the kinds of hardware that we could stick onto a chip, roughly 1.5 times once every couple of years, and then later on he actually changed that. But this is an exponential. So the graph here has a logarithmic y-axis. So this is really kind of an amazing statement. And the 4 dots that you see there are 4 data points that he knew about when he wrote the paper. And later he writes another paper in 1975 that corrects for a slight change in technology. And that 1975 paper, doubling something every 18 months. I don't know whether it's computation, the number of transistors we can pack into a single chip, or things like that. Something gets doubled every 18 months. And then all of a sudden we stopped hearing about Moore's law. And we noticed that when we bought computers, they're capable of only smaller increases in power. So for a long time, we'd buy a computer, and then a couple years later, we'd buy another computer, and it would be much peppier. And now if we get a new phone, which I effectively call a computer, the phone isn't any more powerful than it used to be. At the same time, Bob Dennard wrote a paper talking about the design of transistors. And he's laid out a sort of a paradigm for thinking about transistors and how we could make them smaller and smaller. And he predicted that we would be able to make them smaller for quite a long ways, and that we would be able to take the devices that are constructed from those transistors and scale them down as well, as long as we lived within certain basic boundaries, certain rules that would govern the way. And so those were early statements. Those are 1975, and they're kind of brash statements for the time, and we've lived by sort of those rules for a very long time, 40, almost 50 years. Now, in 1979, Carver Mead, who is the person who gave us Moore's law, he actually coined the term Moore's law. Carver Mead and Lynn Conway got together, and they wrote an important textbook for just the everyday man, the Introduction to VLI Systems. And this was a revolution. It talked about how we could design computer chips using rules that were basically laid out by Bob Dennard, and said, if we live within these rules, then we should be able to take designs we build this year and scale them down so that they're smaller and smaller. We should be able to scale these down as much as we want, provided the technology improves according to the laws that were laid out in those early papers. And this is a revolution. So when this book comes out, everybody starts designing VLSI chips. At the time the book was coming out, we really were only able to design chips with, say, 1,000 transistors on them. Nowadays, we build chips with billions of transistors on them. So this one text has sort of driven the academic way along that route, and it had an impact on the industry at the same time. Now, unfortunately, recently we've discovered that there's been sort of a problem on the horizon, and now the horizon is here, and that is this notion of dark silicon. So in 2011, a couple of different research groups began to realize that while these transistors were continuing to get smaller and smaller, they were starting to change their properties so that the density of the power that was being dispensed with was growing in a way that it hadn't before. Before, the power density had been constant, and then all of a sudden we had passed a physical threshold where the static power dissipation due to transistors was starting to increase. And there are 2 basic types of power. There's dynamic power consumption and there's static power consumption. Dynamic power consumption is what we expect from computation. We know, for example, that we have to use power in order to do any kind of computation. And that's typically thought of as being dynamic power. But the static power is a side effect of the technology we're using here in silicon. And the static power for a long time was just a small term in the equation. And now static power is the majority of the power that we consume when we run a chip. You can think of it as the transistors are little water wheels, and the power is the water going through these water wheels, and the power is just simply the electrons are trying to spin this water wheel, but the water wheel is getting more and more porous. It leaks more than it does computation. And so that's the state we're in. So we can only afford now to turn on some of the transistors. And by some, I mean a very small fraction. So some are estimating today's computers use somewhere between 10 and 15% of the transistors that are on the chip. And that's just because of a thermal budgeting constraint. We don't want our phone in our pocket to heat up. We don't want our laptop to run its fan all the time. So there are thermal constraints, and the static power consumption has gotten to be great enough so that those thermal constraints are starting to be violated. So we can only turn on 10, 20% of the transistors that are available to us on the chip. We can still put more and more transistors on chips every year. So that part of Moore's law is still in effect. In fact, chips are allowing 3% more transistors every year. But the question is, how are we going to use them? We can't turn them all on at the same time. So for example, you can't use parallel processing, right? So parallel processing is great for solving many problems, but only if you have a refrigeration system to go along with the computation. With your phone, you are only allowed to turn on a certain number of transistors, and you've got to make the absolute best use of those transistors when you turn them on. So Michael Taylor, who was at San Diego at the time of this paper, the 4 horsemen of the apocalypse are coming to dark silicon, and what are we going to do with these? And so he laid out 4 different paradigms. And one of those paradigms is to think about building lots and lots of special purpose, little tiny chunks of silicon that do special purpose kinds of computation that we can turn on for just intermittently to solve problems in specific ways. All right, so we're in these dark times. We have built the ultimate general purpose processor. It is not possible to build a more complex processor that will solve the problems any faster or more efficiently. Everything that we can think of doing is going to give us fractions of a % more improvement. We basically are not able to add any more bells and whistles on that. And that's been the case for a while. And it's one of the reasons why we have multi-core processors, is because it became evident to Intel and other firms that we shouldn't spend our transistors just building more processors on building more complex processors on the chip. Maybe a better way to spend those transistors is just to add more processors. So if you knew how to use the processors, you could use them. But if you didn't know how to use the processors, then you might be in trouble. Today's chips are masses of just leaky transistors, most of which are turned off. I've got to move your faces out of my way here. Most of which are turned off. A majority of the computation is wasted figuring out what to do and not in doing. So for example, if you've got a processor and you're writing a program for this processor, about 90% of the computation, the power used to push a computation forward, is invested in decoding the instructions. Now, decoding the instructions that somebody lays before you is not actually doing the computation. So we can think of this as being 90% overhead, and only 10% of what's left of the very small amount of power that we can use is actually going toward pushing the computation forward. So the idea is that we've got software taking off. Everybody's writing software, and the hardware is not able to keep up anymore. And so the gap between hardware and software is widening, and this is a serious problem. So, in 2017, the Turing Award was given to John Hennessy and David Patterson. And these two are responsible. This is the textbook that we use here at Williams for VLSI design. This is the 6th edition. This is the most important textbook in this area. And they have designed, between the two of them, 3 or 4 different processors which have had commercial importance in our field. And these processors are popular. And they have blazed trails. And in fact, they are building new processors which will blaze trails into the future. If there are any architects on the planet who know exactly what state we're in, it's these two. In their book, they say the lazy boy programmer era of relying on hardware designers to make their programs go faster without lifting a finger is officially over. So if you write a program and you want it to go faster, you just waited around for new hardware and it would just automatically go faster. And they say that's over. All right, so here's Moore's Law. The blue line is what it was predicted to be. This is the 1975 version. Notice that we have a logarithmic axis on the left. And the density of transistors that are actually used in chips today is shown by the red line. And the difference between the blue line and the red line suggests that there is something wrong with our engineering paradigm. We're getting this widening gap where we're not able to sort of keep up with the law. And the law is, I think, has been for almost 10 years now over. Now, we can think about it in another way. So we could build more and more transistors by putting them on the chip, by shrinking them down. We call that technology change. We call that technology the process. And the process has changed considerably over all of our lifetimes. We see the red curve tells us essentially the technology, the process that's being used. We are now way down to around 8 nanometer design size. That means that if I take my pencil that I draw my chips with and I draw a pencil line, that means the line is 8 nanometers wide. That's an incredibly small value, and I'll let you think about what that could possibly mean. But many of the features of transistors today are measured in thicknesses that are just numbers of atoms. So maybe a half a dozen atoms thick of whatever material we're talking about. At the same time, the blue line is telling us the power density. It's how much power that we're sinking into each square nanometer within the chip. And we can see that since 2009, say, that that power has really started to take off. The power density has started to take off. And the combination of these two graphs is really a manifestation of dark silicon. And so Patterson and Hennessy, Hennessy and Patterson, when they gave their Turing Award lecture, they said, this is a great time to be an architect. They said, we don't want to be an architect when life is easy because nobody ever comes to us with problems. But now is a great time to be an architect. And in fact, we believe that this is a new golden age of computer architecture. And they had some basic ideas how that could happen. The first thing is we're going to design hardware and software at the same time. We're going to build hardware and software to solve the problem, not as independent efforts. You're at Intel and I'm at Williams College, but together the hardware and software are going to grow together. And so that means the hardware engineers are able to make use of features of the software workflow, and the software engineers are confronted with the basic problems of hardware design. For the first time ever, we now have free and open architectures, and we have open source implementations, not of software, we've had that for a long time, but of hardware. So we now have chips whose designs are completely out in the world and free, and they are being used by people who make your cell phone, for example. So these are new times where people who are just walking down the street, they don't have to live in Hillsboro, Oregon, can design computer hardware to solve problems that they need solved in very specific ways. The way I design hardware may be different than the way you design hardware because my problems are different than your problems. we're going to use this idea of agile chip development. So in software engineering, we have this notion of agile software development where we quickly turn around attempts at building software, and the goal is to get group work, open source, turning over many versions of software to get progress made. And now that process is being applied to the design of computer hardware. And again, they say, this is great. This is the democratization of hardware design. We no longer have to wait for Intel. We can design our own hardware and have it fabricated for us. By the way, we have to wait for Intel because we would have had to wait for Intel because Intel has not been able to deliver on many of their most recent milestones because the technological problems are just so great. So the answer is not building more complex processor. It's building simpler processors that are very specific to the kinds of problems we'd like to solve. So my group here is interested in the development of what I call personalized hardware. We build evolutionary architectures. So we take open source hardware and we add on features to the hardware that some people might need. And the underlying computational fabric that we use is field programmable gate arrays. These are sort of the stem cells of hardware design. These are arrays of gates that can be reconfigured at a moment's notice, and they can shapeshift between one kind of hardware and another. They're basically just a very low-level concept of a programmable device. But they're extremely flexible and they're sufficient now so that for under $10, I can buy a chip that can have multiple processors on it that I get to design. The hardware and software live together on our processors in harmony. And so if you decide that you want to use software, you can use software. If the hardware decides, wow, we've been spending a lot of time using the software to do this, maybe we should turn on hardware. The hardware can turn parts of itself on or off to solve problems. The decision to make hardware take over the computation is one that is based on the pressures of performance. I need to get a problem solved faster, or more likely, I'd like to have the problem solved in the same amount of time, but using less power. So our goal is to, now I've got to move you again. So I apologize. I have a goal. Let's imagine what that is. I'm going to now reduce you to almost nothing. Okay, so the goal here is, of course, hardware personalization. So we want to be able to build hardware that over time becomes very accustomed to the kinds of software workflows that you present it with. My students are, of course, what make the group work, and I've had a large number of students. These are the students that have worked on this particular project, and we've been working on this for several years, and I thank them for all their work. We're going to see a lot of their work as this talk progresses. So Josh Kang is a graduate last year. He's now at Berkeley. He's working with open source hardware design teams at Berkeley. And he and I worked on, and others worked on, this notion of this evolutionary architecture. So at the very bottom of we're going to call it the stack, is the hardware. And at the top of the stack is this operating system. In between is a very thin layer of software that makes decisions about whether or not some particular operation you want to perform should be executed in software at the operating system level, or maybe tomorrow we decide that it has been used so much. Maybe it's an image enhancement algorithm and you've been doing a lot of work with images. So tomorrow the hardware gets turned on and mysteriously your image enhancement runs faster or uses less power. So we've built the infrastructure for doing this, and it's our great hope that this is going to work out and solve some of our problems. But in the big picture, what we are thinking about is that this software layer in the center here, this what he calls SOAR, is going to have these little, it's going to have a little vector, a little list of different pieces of hardware software combinations. we're going to collectively call these accelerators. This list is going to be sort of the DNA of the hardware that we're currently using. And so our idea is that we're going to have this DNA, and this DNA mutates in a variety of different ways to meet the specific demands of the user and to analyze and adapt to the unique physical constraints of whatever the programming or processing environment is. It's truly customizable, and over time we can think of it as being evolvable hardware. And so that's our mission, is to build architectures that can do that kind of thing. The way you might see this happen is you can download not only software from the App Store, but you could also download hardware that would make software run faster. And at night, while you're plugging in your phone, the phone reconfigures itself to be new and more adaptable hardware, more accountable for the resources it uses, and using less power, running slightly faster than it did the day before. And that's just through this process of evolution. We have the technology to do this now, and this notion of open source hardware that Hennessy and Patterson had suggested is exactly what we need to sort of bring this out into the world. So we have this single initial configuration, and your phone could be configured into an endless variety of configurations of software and hardware. Not all of these configurations might fit on your phone at the same time, but we could pick and choose and decide to use one or another based on just our usage patterns. So the pressure of the way we use the hardware is going to cause the hardware to modify itself to adapt to be most efficient for our particular use. So I'm going to show you a couple of applications, and these are just beautiful little pieces of software, and they perform dances. So the whole theme of this talk is dances. At the same time, hardware also performs dances, and they provide each other entertainment, I guess you could think of it. And these dances are now going to start to migrate from being beautiful software dances to beautiful hardware dances. And the beautiful calliope that is hardware is going to manifest itself as new features that are available in software. So I'm going to show you this first problem is from Bob Floyd. He's a 1978 Turing Award winner. Turing Award is the Nobel Prize of Computer Science. And the problem is this: you have, say, in this case, 11 blocks. By the way, you can download this sheet for your own use at the URL indicated. You have, in this case, 11 blocks, and these blocks are listed with numbers on their faces that indicate how much area is used by the face in that block. And what Floyd said was, look you think you want to be a graduate computer scientist at Stanford? Do you think you want to be a junior faculty member at Stanford? Tell me how you would use the computer to partition these blocks into two piles that, if stacked on top of each other, would be as close to the same height as possible. So it doesn't take too much effort to realize that the height of each of these blocks is the square root of the face value. But that's it. That's the entire problem. There's not really a lot of work that has to go into it. You just simply have to come up with some approach for solving this problem. And so this is a problem which we actually use in our introductory data structures course, and we've been using it for many years. And we do this to exhaustion. We actually take a look at all of the solutions, and we can solve this for the 11 block problem. In the handout, you can print at home, you can cut these blocks out, and I will give you 1 minute to solve the problem. It's hard. You probably won't solve it in 1 minute, but you'll get a little bit of a sense of what it means to be a programmer and be confronted with this kind of problem. So that's the problem. And one way you could do this is you could color some of these boxes black and some of these boxes white. And we could think of it as just being patterns. If I laid them out 1, 2, 3, 4, 5, patterns of white or black blocks. I'm going to think of them as bits because I'm a computer scientist. And so these patterns will become little strings of white and black. So this string here has 3 white blocks and 1 black block. So that's making, in the 4 block problem, it's suggesting that maybe we should put 3 blocks in one tower and 1 block in the other. the order in which we explore this space is going to be important, because when n gets to be really, really large, it's not going to be like the 11th case. It's going to be like the 100 case. And we're just not able to exhaustively solve that problem. So if you've only got 10 seconds as a programmer, or you've got 1 minute as a human to try to arrange for these things, you've got to be organized about the way in which you explore the space. And there are lots of ways that we could take a look at all the different combinations of white and black bits, but some are better than others. Now, Aaron Williams and Brett Stevens, Aaron's here in computer science, came up with this really innovative idea about how to generate all of the 2 to the n strings that are length n. And it's just a beautiful thing. It's described in this first sentence. I'm not going to go into it, but just suffice it to say that the first couple of sentences here, anything that can be described in a couple of sentences that does something complex is beautiful. So this does that, and the innovations here allow us to do that exploration very, very quickly using just a few instructions inside the computer. I call this kind of code French chef code. It's not the kind of code that anybody is going to be writing, but we just need a couple of French chefs in the world, people like Aaron Williams, who will come along and say, look, I've got a really fast way to generate all the combinations of white and black blocks. You can run this for 10 seconds and see which of the towers is taller and make some decisions about whether you want to keep this as the best one or not. So that French chef code is just gorgeous. It's beautiful. It dances in this really unbelievable way. So that was a huge innovation, and it means that we can generate strings by exploring this space in not one, not two, but a huge variety of different ways. So if we don't like just counting, which is one way we could explore the space, we could use a cool technique, or they call it a cooler technique, or they even have a technique called the coolest technique. So there are 3 different approaches. So what we did was we approached Aaron, we said, wow, you've got these instructions that run really fast in software. We want to make them dance in hardware. And so Maddie Burbidge last January, she's class of 22, last January came to me and said, what can I do? And I said, well, let's work on this piece of hardware that generates all of these bit patterns as fast as it can. I mean, I think in Aaron's case probably is some of the fastest code for generating combinations with particular properties that's out there. And so if you could make this go into hardware, then we could probably do one of 2 things. We could make it run faster, or we could make it use less power. Or wait a minute, there's a third thing. We could make it run faster and use less power. So Maddie went to work and she got this piece of hardware built in January. And then in February, she wrote a little paper about it. She submitted it to the Grace Hopper Conference and competed in the poster competition for Grace Hopper National Conference in Computer Science. And we're proud to announce that Maddie has won the Undergraduate Research Award from the Grace Hopper Conference for her poster presentation. So this is just one reason why it's wonderful to work at places like Williams, because many students have these capabilities, and we're just so proud of these kinds of accomplishments. So this is the idea. We've got cool, cooler, and coolest. These are just several different ways of exploring the space. And Maddie's hardware is really innovative in that it supports all of these different combinations with just a little set of parameters. Now, the open source CPU, the processor we use, is called the Rocket Core. And we can insert special instructions that tell Maddie's coprocessor here to turn on and generate the next sequence. So maybe we've got this pattern, four black blocks and 2 white ones. We can send a note to Maddie's hardware, and she immediately sends back another note saying, this is the next item in the sequence. So the length of time it takes to do that is effectively the length of time it takes to execute one instruction. So this is actually much, much faster than even Aaron's implementation. And her analysis of this is that she can get speed ups of up to 10 in some cases, maybe even higher, depending on the size of the strings that are currently being generated. The cool thing is that the blue line, which is cool, runs pretty fast. The cooler red line runs even faster, and the coolest line runs the absolute fastest. And so these are just phenomenal new accomplishments in hardware-software cooperation. This is going to be the ultimate French chef software. We're going to just simply call hardware with specialized instructions on this particular core to do these particular things. So if you use Maddie's hardware, you could run the Two Towers problems for 10 seconds and accomplish maybe 8 to 15 times as many explorations as you might have been able to before. The next thing I want to talk about is Knuth's exact cover solving problem, and this is called dancing links. In this place, about 20 years ago, we opened up the Morley Science Center. Don Knuth came and gave a talk about dancing links and introduced the idea. It was a beautiful talk, and what this idea is that we have some problems that we need to exhaustively scour the space for solutions. And he just came up with a paradigm for organizing exhaustive searches. And this paradigm is just, it's beautiful. It's a dance. It has a data structure at the center of it that just does one particular thing, and it does it very well. It does it very fast, and it does it very many times. So here's an example of the type of problems that Knuth might be able to solve. You've got the Sudoku puzzle, which is Knuth's Sudoku puzzle. It has, of course, pi, so 3, 1, 4, 1, 5, 9, 2, 6, 5, 3, and so forth. Those are the squares you're given in the Sudoku puzzle. You've got to figure out how to solve it. It takes me forever to solve these puzzles, but we would hope that we would be able to exhaustively scour the space of solutions, possible solutions, to identify a solution relatively quickly. This is, of course, just another toy problem, but there are many problems that are similar to this. All of them can be transformed or mapped to Knuth's dancing links approach. So what we're going to do is we're going to take this Sudoku puzzle and we're going to convert it into a pattern of rows of black dots that are going to cover the red dots up at the top. So in this case, I'm looking at just some small portion of the Sudoku solver. This says this dot in this first column is trying to identify who goes into this cell. And apparently, I haven't looked at it. There are 3 choices, and the 3 choices are something like 7, 8, and 9. And then the next cell over it has only 2 choices, and the choices there are 8 and 9. And so each one of the little dots in here encodes some little constraint, and the dancing links algorithm is just doing constraint satisfaction. So we're looking for a collection of rows that, taken together, completely cover all of the red boxes without overlap. So that's what the algorithm is supposed to solve. And Knuth's algorithm, I'm not going to go into the details here, but on the inside, it has a list of all of the possible things that could be part, all the possible rows that could be part of the cover. And it keeps them in what we call a doubly linked list. There are 2 connections between each of the elements, one going up and one going down. And at the very beginning, we see the original has all of these things. And we're sure that this is not a possibility because, for example, 4 and 2 collide with each other. So 4 and 2 should never be in the solution at the same time. So anyway, in 136, our second semester course in computer science, we say, if you decide that you're going to take 2 out of this linked list, the appropriate thing to do is to take 2 out, link 1 to 3, and then tell 2 it shouldn't be holding on to anybody at all. That's what you should do. And what Knuth's big idea was, just let 2 continue to hold on to this sort of chorus line of options that are dancing together. So 2 continues to hold on to 1 and continues to hold on to 3 because sometime later it might need to be reinserted into this list. And so here is what the beautiful dance looks like. We start off with this original linked list and we decide, I'm going to call this operation, by the way, of pulling 2 out here or pulling a single element out of here. I'm going to call that a pleating operation. So it gives you a sense of the physics of what's happening here. I'm taking 2 pieces of fabric and I'm pulling a little pleat out of here. So we're going to take this original list and then we're going to pleat it at 2. So it looks like this. This is the list we saw earlier. And then we're going to pleat it at 5. And then we're going to pleat it at 4. And we get these beautiful structures. The white boxes indicate what are still viable options for the cover, and the black options are things that are currently held to one side because the exhaustive search would not necessarily admit those at the same time that they would admit the white options. So, but what's interesting here is to take a look at the fine structure of what's coming off of the side of the list here. It's basically a little polygon, each of which is, that polygon is somehow getting triangulated. So if that means something to you, you can kind of see what the beauty is. Here I've pleated again at 7, and then I might decide that I'm going to unpleat. So unpleating just is the opposite. So 4 was pointing at 3 and 6. So it injects itself back into the doubly linked list between 3 and 6. And notice that 5 is now touching exactly the elements it needs to in case it needs to be inserted. So what we decided to do is to hire Maddie and say, hey, can you build this pleating and unpleating operation in hardware? And she did. And it turns out that during pandemic times, students can actually get a lot of work done from remote, and they can get computers to do a lot of work done on their local machines. So here is a sort of a diagram of all of the different options of searching through the Dancing Links code. Each of the little leaves in this tree, we think of this as a tree, the leaves are the fringe here. Each little fringelet, every little place where we see something hanging down, something is pleating or unpleating. And it turns out that in this algorithm, 14% of the time is spent pleating. And if we use Maddie's hardware, we can speed up that pleating time by 5%. We're in the process right now of measuring power consumption, which is very difficult. These operations are extremely fast, somewhere around a microsecond, and we need to figure out how much power is being consumed by that operation through dynamic power consumption alone. What's interesting about this is Maddie's hardware will make this algorithm run faster no matter what the problem is you're trying to solve. So Knuth's Dancing Links algorithm is beautiful because its dance is applicable no matter whether or not you're solving Sudoku puzzles or you're trying to pack boxes into a mail truck or whatever sort of computationally difficult problem that you have to exhaustively search. A lot of typesetting problems, for example, are solved this way. So we just do exhaustive search. We can speed this up by 5% by just adding a little tiny piece of hardware, and we might even save some power. So I'm going to talk about dances in Manhattan. So this is the micrograph I showed you at the very front slide. And this is a micrograph we took here at Williams of the Intel 8088. And this is the chip that was in the original PC. And what we're looking at here is an indication that this is the microcode associated with this PC. Whoa, what is microcode? It must be small. Yes, it's small, but what's more important, it's code. It's software. So inside this chip that we would normally think of as being hardware, there's actually a large section of the chip that's just dedicated to software. And if you look very closely, I can see you all looking very closely, but if you look very closely at this, you'll notice that as soon as you see a pattern, it gets interrupted. There's irregularity in here. Where you see irregularity in hardware, it's a sign that something is really software. So the software has injected itself. This chip is complex enough so that the authors didn't know how to build it completely. And so they left a little bit of, the arrangement of the levers and wheels and the calliope to be designed in software that was dropped into the chip at the very last moment. Notice here also that everything is sort of square. It either goes north, south, or east, west. It's got sort of a Manhattan network. Here are some devices we've constructed here at Williams. For the 40th anniversary of the 4004, the first chip, we built a 4004 in what we call sustainable CMOS. And I've drawn a little red box around here to describe what area of the chip is responsible for control. So this very old chip is complex, but what was really most complex about it was just how all of the parts work together. And so almost 50% of that chip is software. The middle chip is the 40th anniversary of the 6502, which is the basis for the Apple II processor. And I've drawn again here, this is our implementation. I can't divulge any of the details about the actual implementation of the 6502, but in our implementation, we have microcode, and you can see that it's irregular. but basically there are a bunch of instructions from the top to the bottom, and there are wires that go from left to right that control different units in this processor. Without the software, the processor would just destroy itself. The units would not be synchronous. Life would be less than exciting. We see here that software has again invaded the hardware. On the right-hand side here, we have a reduced instruction set processor. This is one of the processors that Hennessy and Patterson had advocated for in the 90s. And they said that wonderful thing about this is these processors are so simple, their control is easily described, and they run very, very fast and efficient because of that. And so we can see here the control unit for our little Williams RISC processor is just a fraction of the entire device. But notice how everything goes north, south, or east or west. Now in, I can't remember what the year is, but at the time when we were talking about 2048, students were playing a lot of the game 2048. I got tired of them coming to my office during tutorial and playing 2048. And so I said, let's build ourselves a 2048 processor game console. So this is a 16-core processor. It's very small. This is less than 2 millimeters on a side. 16-core processor, and the control for it is just this lower left-hand corner. This has just got beautiful dancing that is exactly the kind of, the inside the hardware is exactly the reflection of the tiles moving back and forth in the 2048 game. If you think that's a beautiful game, then you'll just think that this processor works in a beautiful way. On the right, we have our field programmable gate array computational fabric. We designed some here at Williams. And the interesting thing is here that there is no control. So this is a piece of hardware that can shift, shape shift, and become different things by downloading some bits of information. But effectively, there is no control anywhere throughout this fabric. And it's a liberating piece of hardware because it allows us to take, for example, the hardware on the left, and we can make this hardware on the right act like the hardware on the left if I want to, or I can go back to one of the previous things, embed some other processor. I can make a different decision every day of the week and reconfigure it every time. Now, this is the latest processor we built. Somebody came into my office and they said, hey, I'm mining Bitcoin on my phone. There is no way that anybody should be running Bitcoin mining software, well, software of any kind, because you're just not going to be able to mine. You're not going to be competitively mining Bitcoin. I'm not a Bitcoin miner, but I got so tired of seeing students waste their time trying to mine Bitcoin. I said, let's build hardware. So the algorithm for doing this particular kind of algorithm is open source. And we just simply took the algorithm, we embedded on a chip. This is one of the most amazing devices we've built at Williams. It's fully pipelined. Every unit in this device is working all the time. So the sequential nature of the software turned into highly parallel features in the hardware. The control is just this little tiny bit here, and you can see I've blown it up. The irregularity, again, of the control unit suggests that this is really software. The software is sort of determining exactly how all of the agents who are working in the pipeline of computation, this is an assembly line for computing something. The data goes in through the left and out through the right. How that happens is all governed by this control mechanism here on the upper left. So that's just absolutely beautiful. This device is 30 microns on a side. In today's technology, 30 microns, that's just incredibly small. You would need an electron microscope to observe any sort of detail in there. Now, my big goal is to think about what it means to compute generally. And so I say, well, you know, we have to get ready for a time when we're going to have biocompatible computation. We're going to have to deal with two things. First of all, we're going to have irregular connections. And the other thing is that we're going to have to deal with error. So if we're going to build a pacemaker out of the patient's own heart material, then we have to be able to figure out how we can connect the heart, which has a very irregular shape, different parts of the heart together with whatever technology we're using. And we have to be ready for the fact that it's a wet lab experience. There are things that can go wrong. It's not always going to work. And computer scientists just hate, like business, uncertainty, right? So we don't want to write algorithms that lead to uncertain results. but we're going to have to confront that issue soon. And I'm just going to say one word, plastics. No, I'm going to say one word, Mookie Betts. That's 2 words. No, I'm going to say one word, CRISPR. So if CRISPR means anything to you, it means that computer scientists are starting to edge their way into the cell. And we're thinking about ways in which we might be able to program things going on in there. And we have to be ready for the kinds of problems that might occur. So Catherine Lindsay, a student of mine, a class of 7, worked with me on trying to play the game of life. Now, for some of you, you may know what the game of life is, but it's just simply a very simple simulation where we simulate a whole bunch of cells, and these cells are regularly connected as they are on graph paper, and these cells communicate back and forth with their neighbors, and they make decisions about what they're going to do, whether they're going to be black or whether they're going to be white or so forth. And the cellular automata, which is on graph paper, that's very interesting. We know that we can build very simple cellular automata that are as powerful computers as any computer we have on the planet. And the question was, could we do something not on a regular lattice? Could we do something that relaxes the regularity in some way? So what we did was we took Penrose tiling. So these are aperiodic connections. So this is square graph paper where the squares get kind of pinched, and all of a sudden, instead of having 4-fold symmetry, in certain places they're 5-fold symmetry. And it's not periodic. So as soon as you see a pattern, if you sort of scoot across and you see like maybe a couple of stars in a row, then the star pattern will be broken because these are aperiodic. There's no periodicity. So we wanted to look at this because this would be the first difficult problem for programming. And so what we did was we played the game of life on these aperiodic tiling. So for those of you who are physical chemists, this could be a quasi-crystal. We figured out how to do computation on the surface of a quasi-crystal. So what I'm going to show you here is something called a glider. If you don't know what this is, I encourage you to Wikipedia it. There's tons of material about this. This is a collection of inhabitants of this world that just slide along together based on local rules. They make decisions about whether they're going to move to another cell or not. And the black cells here are team leaders, and the gray cells that are around them are part of their team. And collectively, they develop a kind of a robustness in the computation that is a little bit unexpected. So this is the game of life. I'm playing several different generations. And the cool thing here is that every few steps, every 4 steps, we see this particular pattern. This is a reproducing, self-reproducing pattern, which is available on the surface of something that is not Manhattan. So that's cool. We can do computation robustly on aperiodic tilings. The next question is, can we loosen the rules even more? And so we heard that David Peek and Keith Mott at Utah State University were looking at some plant leaves, and they were trying to figure out how to measure the temperature inside the leaf in a non-invasive way. And what they found out was that over time, these leaves were exhibiting temperature patterns that suggested that they might be performing some kind of computation. Now, what happens in a leaf is we have these little cells, these stoma, which are responsible for gas exchange. The stoma can either be open, in which case gas exchanges with the outside world, or the stoma can be closed, in which case it holds onto the gas and stays warm or stays cool, whatever it needs to do in order to thermal regulate, in order to transpire, and so forth. So it's interesting because these devices here are these leaves do not have any sort of neural connections inside them. They're not able to communicate in any fast way amongst themselves, and yet these patterns were setting up and apparently were making decisions about whether a majority of them wanted to be open or whether a majority of them wanted to be closed in a particular environment. Say a high humidity environment, all of a sudden the stoma sit there and they say, we've got to make a decision about whether we're going to open or close. They were making that decision quickly. And so what Tony Liu, who's now at the University of Pennsylvania, and I did was we took a look at networks of these stoma, and we modeled the same kinds of computation that we saw in the game of life. And we found out that these devices actually can, leaves can actually support a computation. We don't yet, as biologists, know the mechanism. We think that the gases they exchange are contributing to their neighbors' decision making. But we look at the irregular networks of these computations, and they seem to be quite resilient. In fact, they're so resilient that Tony went in with scissors and cut out some of the parts of the leaves. And what's interesting is you can cut these leaves in half and they will make the same decisions whether or not they're connected. So there's no nothing in the matrix that is actually helping them make these decisions. So we're beginning to identify what it is about computing in hardware. What is happening here that makes this computation robust? And our goal here is to see, can we start to move on to hardware that is reconfigurable in new and different ways, that is something you might be able to grow in a pot. And so these leaves are making decisions. We can think of them as performing some sort of computation. And those computations appear to be robust. And that is good news for computer scientists who want to be able to leave silicon and move into other kinds of biocompatible materials, because it looks like we might be able to have some environments that we can at least do some very simple computations on. So we design processors that evolve. We have notions of hardware and software, and those notions are evolving. The hardware is generally softening. It's becoming more agile in its development. It's open source. It's reconfigurable. And the software is, in general, hardening. It's becoming like the microcode on chips. It's also agile. It's also open, and it's also reconfigurable. In short, the boundary between software and hardware is blurring. If I look inside a cell and I ask you, is DNA hardware or software? Are the macromolecules hardware or software? You would be hard pressed to say exactly which is which, because both of them play the same roles. They're just doing different kinds of things in their purpose. So the software is blurring, hardware and software are becoming one, and we're trying to get used to that world. It's a great time to be an architect. Thank you very much. I'd be happy to take questions. You can just unmute all of yourselves and yell them all out, or you can type them into the chat window. Be happy to talk to you.
Thank you very much, Dwayne. Thanks for a great lecture.